Well, hello, everybody. Welcome to our third installment in our seminar series. We're really excited about the presentations that we have tonight for you. And A3 Vice President Eric Peitsch will introduce those in a minute. My name is Dan Caveney. I am the Executive Director of the American Avalanche Association. Before I get started, I like to always give some credit where credit is due. We've been working really hard to make sure that everybody's got access to some great information during this period of isolation due to COVID, and we could not do that without our sponsors. And so I just want to open up our presentation here by mentioning all the great help we get from our sponsors. And you can see a graphic here that has them all lined out. CIL Explosives is a great friend of ours, and they donate a percentage of the money they earn with avalanche mitigation explosives in the U.S. to us. Backcountry Access, longtime supporter. MND Safety, who used to be TAS. Veasan Avalanche Control and Peeps have been great supporters of A3. We have some new supporters as well. Major supporter Onyx Maps, who is just releasing a brand new mapping app that you can use to navigate in the backcountry. Arc'teryx, and our newest major supporter, Flylow Gear. So again, I encourage you to talk these guys up and patronize them when you can. They're really they have some skin in the game with the community, and they help us do things that we think help support the Avalanche community. With that, I'm going to ask A3 Vice President and tonight's moderator, Eric Peitsch, to come on board here and announce our first speaker. Eric?
All right, thanks, Dan. Appreciate it. And thanks to all of you for joining us this evening. I hope the winter is going well for you. And I hope you've been enjoying the virtual seminar series thus far. Please send any feedback or any ideas of any topics that you'd like to see addressed in this series. Well, actually send me the positive feedback and then send Dan the constructive feedback. But we have the topics lined out for the next two sessions, but we hope to continue this next winter as well. So please send any ideas or anything you'd like to see. So I'm excited about tonight's session. We all know that weather drives avalanches, but climate drives weather, and taking a look at the relationship between avalanches and climate is particularly important in the context of a changing climate. So we're going to learn more about this tonight through three great talks. First, we'll have Pascal Haegeli. And so we actually were scheduled to have Brett Chandro present for us. But unfortunately, because COVID is COVID, there were some complications with Brett's work schedule, and he's filling in for a colleague. So we have Pascal joining us. Pascal is a co-author on the work that he's going to present tonight. And we all know Pascal from last month, when he presented on airbags. And let's see, just a brief refresher if you weren't able to join us, but Dr. Pascal Haegeli is a professor at Simon Fraser University, where he holds the NSERC Industrial Research Chair in Avalanche Risk Management. And his research interests are at the interface between the natural and social sciences. And his favorite projects are close collaborations with industry partners. He currently supervises a team of 10 graduate students working on a variety of avalanche safety topics, ranging from snowpack modeling to terrain analysis, as well as risk communication and education challenges. So Pascal will talk to us tonight about using avalanche problems and looking at large-scale atmosphere-ocean oscillations in Western Canada. And remember that if you have any questions, feel free to put those in the Q&A, not the chat. And if you would like to ask a live question when the presentation is over, just use the raise hand function. So over to you, Pascal.
Thanks, Eric. And thanks to everybody for having me again. As Eric said, this wasn't really the plan. I'm really here on behalf of Brett, who is a former student of mine who's currently stuck in northwestern BC at a mine site, and the connectivity is just not good enough to present to you guys. So let me just set up my screen here. And you should now, see my presentation slides. If you don't, please let me know. So Brett's research, Brett graduated from my program 2 years ago. So this goes a little while back, and I have to say that I'm a bit rusty on the whole topic. So please bear with me if I fumble my way through some of these parts where Brett is really the better expert. But Brett's research was really inspired by the fact that every fall, country skier and mountain snowmobilers in Western North America are kind of wondering what the upcoming winter has in store. And the big topic is always whether it's going to be a El Nino or a La Nina winter, as there is a fairly decent relationship in large-scale atmosphere oscillation and the quality of the backcountry winter in different areas. In British Columbia, for example, it's the La Nina winters that make skiers and snowmobilers happy, while it's the El Nino winters that get Californians excited. So given the strong impact on winter weather, Brett was curious to explore a new approach for examining the relationship between large-scale atmosphere ocean oscillations and the seasonal nature of avalanche hazard in Western Canada. Since the predictability of most of these most important oscillations is continuously improving, a better understanding of these relationships might provide the foundation for an informative seasonal avalanche forecast in the future. In addition, climate models, and that's how we link to the topic of the seminar tonight, climate models are getting better and better at predicting the frequency and intensity of these oscillations into the future. So having a better understanding of the relationship between avalanche hazard and these oscillations might provide some insight on how climate change might affect avalanche hazard in the future as well. There's atmosphere oscillations affecting the winter weather in the Pacific Northwest and Western Canada, but as I've already mentioned, the most dominant one is the El Nino Southern Oscillation, or ENSO. ENSO goes back and forth between positive phases, which are referred to as El Nino, and negative phases, which are named La Nina. Now, ENSO originates from a periodic change in sea surface temperature in the eastern tropical Pacific, just off the coast of Peru. But it has effects on weather patterns all around the world. What you see on these maps are a simplified perspective on the weather anomalies that are associated with the two phases in North America. For the Pacific Northwest and Western Canada, El Nino winters are generally associated with warmer temperatures, and La Nina winters are cooler and potentially also have more precipitations, at least in some of the regions. Below the maps, you see the list of the recent years where we either had El Nino or La Nina winters. The bold years are the winters when the oscillation signal was particularly strong. So we had a strong El Nino winter in 2016 and a strong La Nina winter in 2011. As far as I'm aware, we're currently in a moderate La Nina winter. In addition to ENSO, we also have the Pacific Decadal Oscillation, or PDO, which enhances the ENSO-related temperature anomalies, and the Pacific North American Pattern, or PNA, whose positive phase is associated with warmer and drier conditions, and the negative phase results in cooler temperatures and more snow accumulation. Another oscillation affecting the winter weather in Western Canada is the Arctic oscillation, which is distinctly different from the other Pacific-centered oscillations. Here, the positive and negative phases are associated with stronger and weaker westerly flows, respectively. The effect on temperature and precipitation is regionally a little bit more variable than in the other oscillations. Now, we're not the first interested in examining the relationship between these oscillations and avalanche hazard conditions in Western Canada. In 1987, Fitzharris was the first to relate large-scale oscillation patterns to major avalanche winters at Rogers Pass. In 2013, Dave McClung published a study that examined 30 years of avalanche observations from Bear Pass and Kootenay Pass, two highway passes with avalanche safety programs in British Columbia. He found that La Nina winters were associated with more snow, more avalanches, and a higher percentage of dry avalanches at these programs. 1 year later, Scott Thumler and colleagues presented a study at the ISW that analyzed the avalanche observations from 6 highway programs in British Columbia. In addition to confirming McClung's result, they found also increased dry avalanche activity during the negative phase of the PDO and increased wet avalanche activity during the positive phase of the North Atlantic oscillation, a close relative to the Arctic oscillation I mentioned before. Now, while these studies offer valuable insights, they also have considerable limitations. Since all of the studies used observations from highway avalanche safety programs, they only represent point observations and cannot really provide a comprehensive perspective of the conditions across all of Western Canada. In addition, the risk from avalanches across these highway passes is tightly managed, which makes the recorded avalanche observations vulnerable to changes in avalanche control practices. In addition, like only focusing on the magnitude of seasonal avalanche activity, even if separated into dry and wet avalanches, is a little bit limited. So we were hoping to sort of add a new perspective to this. The new perspective is that in 2010, the avalanche warning services in Canada changed the way they assessed conditions and how they communicated them to the public. And as everybody here on the call is probably familiar, we've generally, not only in Canada, but also in the US, we moved from a more free-form text description of the conditions to a much more structured approach that explicitly defines what types of avalanche problems avalanche forecasters concerned with, and we ended up with the avalanche bulletin format that we're familiar with today. What you see on this slide is a screenshot of an avalanche bulletin from Avalanche Canada. And what you can see is that on this particular day, we're concerned about a wind slab and a persistent slab avalanche problem. Now, in total, we're using 9 different avalanche problem types in North America, as you can see illustrated on the slide. Quick thanks to the Colorado Avalanche Information Center for the nice graphics here. Each of these problems emerges from a different set of weather and snowpack conditions, responds to changes in conditions in a unique way, and most importantly, requires different approaches when traveling in the backcountry. So the avalanche problem information really provides perspective on the daily nature of avalanche hazard across entire forecast. What you see on this slide is an example of how avalanche problem situations can evolve over a season in the 3 elevation bands of a forecast region: the alpine, tree line, and below tree line. You see that you see the avalanche problem labels on the left, and the colored dots indicate that a particular avalanche problem was a concern during that day. For example, the green dots represent days when avalanche forecasters were concerned with wind slabs. And as you can expect, they were more often concerned with wind slabs in the alpine than below tree line. The yellow dots represent storm slabs, and the red dots represent persistent slab avalanche problems. The colored squares at the top of each chart are the time series of the avalanche danger ratings at that elevation band, but they don't really matter for the analysis I'm presenting here. Now, based on these time series, we can calculate seasonal prevalence values for each of the avalanche problem types in each elevation band. These values simply indicate on what percentage of days a problem type was a concern in a specific elevation band of a forecast region during a particular season. Now, the idea of our analysis was to see whether we could find any meaningful relationship between the seasonal prevalence values and the seasonal strength of the atmosphere-ocean oscillations I mentioned before. What you see on this chart are the average indices for the main winter months, so November to April, of the various oscillations of our study period, which was from 2010 to 2019. Now, because the ENSO, PDO, and PNA indices exhibited very high correlations, so the curve looked very similar, it did not make sense to include them separately in our analysis. And so we therefore calculate an average index that represents the Pacific focused oscillations in general. So we're just focusing on the Arctic oscillation by itself and then this combined Pacific oscillation index. Now let's look at the entire analysis approach for our study. So we have these seasonal prevalence values for 9 avalanche problem types from up to 14 forecast regions in Western Canada for 10 winter seasons. For the analysis, we grouped our forecast areas in 6 main regions, as you can see on this map with the different colors. So we have the Coast Range, the Columbias, and the Rocky Mountains. And for each of these ranges, we have sort of a northern region and the southern region. We then estimated a series of so-called beta mixed effects models to simultaneously explore the relationship between the avalanche problem prevalence and the Pacific focused oscillations and the Arctic oscillations at the same time. For each avalanche problem type, we estimated a model for alpine and tree line and a separate model for below tree line because these different elevation bands seem to respond a little bit differently. For each of these models, we included so-called interactions between regions and oscillation indices so that we would be able to pick up regional differences in their responses to these oscillations. As an example, the chart you see on this slide shows the relationship between the strength of the Pacific focused oscillations and the prevalence of wind slabs in the alpine or tree line for the different regions. The points are the actual observations from our data set, and the lines and the associated bands represent the model estimates with a confidence interval around them. Now, the interpretation of the model parameters that you get out of the regression analysis is unfortunately not straightforward. especially because we have these interaction terms included. So to make the interpretation a little bit more tangible, we use the parameter estimates from the model estimates to calculate so-called marginal means for each region across the range of the observed indices. And then we applied, it's called a post hoc test, to estimate whether there are significant differences from each other. For each of the oscillations and regions, we looked whether the model estimated prevalence values for a problem differed significantly across the observed range of the oscillation index. So basically, we calculated the prevalence on the far left and the far right of the graph, and then looked whether there is a significant differences between those two values. Now, this table gives you the full glory of the results of the 19 different models that we estimated. Each box represents the differences in these marginal means in percentage points for a particular avalanche problem in the alpine/tree line or below tree line, roughly arranged according to the locations of the different regions. Significant positive associations, which are shaded in red, indicate that avalanche problem types that are more prevalent during the positive phase of the oscillation. And significant negative values, shaded in blue, indicate avalanche problem types that are more prevalent during the negative phase of the oscillation. So for example, in the top left corner, you can see that the Arctic oscillation has a significant positive association with the prevalence of storm slab avalanche problems in northwestern British Columbia. Now, this table takes a little bit of time to fully digest, and we don't really have enough time for that in this presentation. So let me give you the gist of our results in a different format. What you see on this slide is the southwestern part of Western Canada with the outlines of the forecast areas. The colors and labels indicate the larger scale areas, that is the spatial focus of our analysis. Now let's look at the effect of the Pacific focused oscillations first. In the below tree line model, the pattern we observed are consistent across all regions. Days with no avalanche problems at all are prevalent during the positive phase, whereas storm slabs, wind slabs, and dry loose avalanche problems were more prevalent during the negative phase of the Pacific-centered oscillations. In the Alpine, wind slabs seem to be more prevalent during the negative phase in several regions, and storm slabs were more prevalent in the Rocky Mountains. We also found that the southern region experienced more wet avalanche problems during the positive phase of the Pacific-centered oscillations. In general, these patterns are consistent with our general understanding of the effect of the Pacific-centered oscillations on the winter weather pattern in Western Canada. Now let's briefly look at the effect of the Arctic oscillation. Here, the observed patterns below tree line were again consistent across all regions. We found a higher prevalence of deep persistent slabs and wet slabs during the positive phase, and a higher prevalence of dry loose avalanche problems during the negative phase. In the Alpine, the most dominant effect was that higher prevalence of deep persistent slabs in the South Columbias and the Rocky Mountains. And we also found a higher prevalence of wind slab problems in the Rocky Mountains in the North region and the South Columbia region. And in the Coast North region, we found a higher prevalence of storm slabs associated with the positive phase of the Arctic oscillation. A fairly consistent pattern across many regions was that we observed a higher prevalence of wet snow avalanche problems during the positive phase of the Arctic oscillation as well. Dry loose avalanches were the only problem type that was more prevalent during the negative phase of the Arctic oscillation in several regions. And to finish up, let's summarize the main points of the study. We used avalanche problem information from public bulletins to capture the seasonal nature of avalanche hazard and relate it to atmospheric ocean oscillation indices. I think this approach has the potential to provide a more comprehensive picture of this relationship than previous studies. Now, while the results are realistic and consistent with previous studies, the challenge of our study is that the data set is relatively short. So we can therefore only consider this study as a pilot on a topic that will require more research in the future. The shortness of the data set has also prevented us from properly isolating the effects of ENSO, the PDA, and the PNA. But I think that a better understanding of these relationships might eventually open the door for a more informative seasonal avalanche hazard forecast that can set sort of general expectations for an upcoming winter. And as I said at the beginning of this presentation, because these oscillations can now be more easily forecasted with climate models as well, maybe a better understanding of these relationships can also provide us with a tool to look at how avalanche hazard might change with climate change in the future. Now, sorry, just a little too trigger happy. Now, if you're interested in learning more about our study and their interpretation, you can find in a manuscript that we're currently just in the final stages of publishing in the academic journal, The Cryosphere. This is an open access journal where everybody can access papers. So you can find it in the URL, which you can see at the bottom of the screen here. Before I wrap up, just a quick thank you to all the agencies that supported our research. And thanks for listening. If you have any questions about this research, feel free to email us, either me or Brett directly. And if we have any time left, I'm happy to take any questions.
Great. Thanks, Pascal. That was an excellent talk. And let's see, we don't currently have any questions at the moment. Oh, we just have one right now. All right, we'll go to that one. We have the question, would adding seasonal precipitation to the model be redundant because you are already modeling the oscillations?
We were really our main objective was to see how we can tie it to these oscillation indices. We're basically trying to piggyback on all the good work that atmospheric scientists are doing and seeing whether we can use that to our benefit. Of course, if we included precipitation into these models, we would be going more towards actually modeling avalanche hazard directly, which is a whole other sort of research path that some of my students are working on. But here we try to sort of keep it as simple as possible.
All right, we have another question here with, so the question is, with global warming do we expect more El Nino years or just more variability?
That is a very good question. And unfortunately, I have to say that I can't answer this on the top of my head. I'm really not enough in that topic directly to give you a good answer. There's lots of information around this online, and you might be able to find something along that answers your question, but I wouldn't feel comfortable to give an answer to that.
We could get back to that question later on, and maybe Ben can add his insight as well.
Exactly.
But we do have a few more questions. So let's see. We have one from Jane that says, all right, due to climate change, how would you be able to account for continuously changing weather patterns? Will you always have a small data set or find a way to adjust for the rate at which the climate changes?
Yeah, like traditionally, like in atmospheric science, they always look at sort of 30-year periods. So that's kind of the time period for defining climate. I guess the challenge for us is a little bit that our practices around forecasting avalanches is continuously changing and improving. And so there we're a bit challenged with coming up with long enough time series that would allow us to really sort of calculate or characterize avalanche hazard in a consistent way. And so I think part of the solution there is to properly document over time how our practices changes, and that would allow you to potentially correct for that in the model. And we actually partially did that in our analysis. So in 2010, that was the first winter that Avalanche Canada really changed to these avalanche problems. And after a winter or two, they sort of made the executive decision that they wouldn't have storm slabs and wind slabs in the same bulletin anymore, that they would just sort of, they thought that it's much easier, or that it might be confusing to the public to have those two problems in the same bulletin. And so they made that decision. And so that automatically changed these prevalence values in our model. And so we actually added an additional factor into our model to correct for that, which is suboptimal, I would say, but it's a way for us to maybe take advantage or create longer time series that we can use.
Great, thanks. So the next question we have is, how close would these models mirror the United States? So El Nino or La Nina. And I think maybe just, a bit of speculation on how those results might mirror, or your results might mirror the US.
Yeah, like, I mean, these effects are really quite regional. And so we found differences within our sort of those 6 main regions that I showed. So I wouldn't sort of want to make any speculations around how this is in the US, but avalanche problems have been used for a similar period of time. So it would actually be quite interesting to do a similar analysis across the US forecast centers and then see what comes out. Like, I think that would actually probably strengthen the whole study quite a bit. Something for another student to do sometime in the future.
Exactly. So unfortunately, we're gonna move on in the interest of time, but thank you, Pascal. That was excellent. And there are a few other questions in the Q&A. If you want to answer those, great. But sure, we'll move on from here.
Thank you.
But thanks everyone for submitting questions. These are great questions. All right, our next speaker is Dr. Benjamin Hatchett. Ben is a regional climatologist at the Western Regional Climate Center in Reno, Nevada, and research professor at the Desert Research Institute. He studies the hydrometeorology and hydroclimatology of mountain and dryland regions at timescales ranging from minutes to millennia in the past, present, and future, using a wide range of observational data and atmospheric and hydrologic models. His specific interests pertain to natural hazards, including mass movements, drought, wildfire, downslope winds, and flooding. A better understanding of maximizing snow quality and minimizing avalanche hazard drove him to study mountain meteorology. So his talk tonight is titled Avalanches and Atmospheric Rivers in a Warming and Weirding World. Thanks, Ben. Over to you.
Cool. Well, thank you guys very much for the invitation to speak before everyone and share some thoughts and insights and try to sum up some of the research that's ongoing on our rapidly changing planet. The first slide here just kind of shows a few examples of interesting events that we've been seeing just in the past couple of years that in the coastal ranges, but in other ranges further inland in North America and worldwide, oftentimes have pretty strong ties to either the prevalence, magnitude, and intensity of atmospheric rivers, or their lack of taking place. And something that we've been seeing that's been something a little interesting, at least in the Sierra Nevada, where I'm from, is when we don't get a lot of these storms, we end up with much shallower snowpacks than normal, and that kind of changes the game a little bit. So we'll talk a little bit about that. So what I want to share with you all tonight, let's see why my slides, there we go, is I'll kind of try to somewhat quickly go through a lot of material. I've tried to make sure that all the things that I cite have links on there, the DOIs, so that you can find those papers and read them if you're interested. You can always contact me and I can get a hold of papers for you if you'd like. But what I'll do tonight is go over the basics of atmospheric rivers, or ARs as they are frequently referred to as, highlight some of the impacts and influences on avalanche hazard, talk about climate projections of ARs, discuss a few other expected and ongoing changes in mountain weather and climate that I'm sure many, if not all of you, have been experiencing, much to our chagrin in a lot of cases. I like to say that I'm trying to disprove climate change, but my lines all point the wrong direction, meaning that things are usually happening in a direction that we're not too fond of. And then we'll finish with a little thought experiment on compounding effects of how the human factor may play into the changing mountain environment with regards to climate change, atmospheric rivers, backcountry recreation, and avalanches. So the official definition of atmospheric rivers, if you Google the term and you come across the American Meteorological Society webpage, you're going to find these images, which on the left-hand side, one shows you the plan or map view image of an atmospheric river. Typically, these take place along the cold front behind the primary warm front and represent a long, narrow, filamentary corridor of strong horizontal water vapor transport, typically associated with a low-level jet ahead of the cold front of an extratropical cyclone. There has been years of debate coming up with this definition. This is what was finally settled on after many exciting evenings and town hall meetings. So when we talk about atmospheric rivers, typically we are talking about these very long, narrow plumes of water vapor emanating from the tropics and being entrained into the warm conveyor system of mid-latitude cyclones. On the right-hand side shows a vertical cross-section. So if we're looking across the atmospheric river, and so the primary plume of moisture is concentrated somewhat low in the atmosphere. This is over the ocean. And so once the plume of moisture starts interacting with terrain and becomes elevated, things will change a little bit. But for a base level view over the ocean, where atmospheric rivers primarily originate, the vast majority of water vapor is concentrated in the lower elevations in that low level jet. And once the AR begins to interact with terrain, that's where the orographic forcing and other synoptic scale drivers of lifting mechanisms will start to elevate that moisture. And that becomes important when we want to get that moisture further inland. If you're just running into a coastal mountain, all is well and good. But if we want to transport that moisture further inland into the intermountain or continental mountain climates, the elevation of that moisture is really important. So too is the presence of terrain gaps, because there's been some nice work showing how moisture can much more easily be transported inland if the angle of the atmospheric river is favorably aligned with large gaps in terrain. So when we look at atmospheric rivers from a weather model or weather forecast model perspective, this image shows one realization of that. This is showing precipitable water, which is just a measurement of total moisture in the atmosphere. And that's what's shown by the colors. And really the state of atmospheric river science developed substantially when the perspective of moisture and wind was taken. And we call that the integrated water vapor transport. So that's where we basically break the atmosphere in a vertical sense down into a series of blocks. We figure out how much moisture and wind are occurring at each one of those little blocks, and we sum that up. And that final quantity is sort of the ultimate currency of atmospheric rivers, the IVT, which is very useful because we can have a lot of moisture, but if we don't have wind, we're going to miss out on a lot of the key precipitation generating mechanisms that are necessary to really produce the notable impacts that atmospheric rivers have, that being extreme precipitation that is typically sustained for not just hours, but at times multiple days. Another view that is commonly shown when looking at atmospheric rivers is that of satellites, which are able to measure the precipitable water. So this is a microwave image of total precipitable water taking place back in 2017. And you can see these long filamentary structures emanating from the tropics. We call that the tropical moisture reservoir, and transporting moisture poleward towards the polar regions. And this is really important because atmospheric rivers, while they only occupy approximately 10% of the mid-latitude regions at any given point in time, they are responsible for transporting roughly 90% of the water vapor from the tropics to the poles. So they have a tremendous role in the global hydrologic cycle. And in many locations, particularly along the coasts, but still too as you move further inland, they are major drivers of the interannual precipitation variability. And what I mean by that is that the difference between an extreme dry year and an extreme wet year can often come down to a handful of these events either occurring or not occurring. And this year being a very good example for comparing and contrasting the southern half of the coastal United States, so kind of southern Oregon to California, where we have had no atmospheric river activity, and we are moving well into drought conditions, and the Pacific Northwest, where they have had above average precipitation and an above average normal of landfalling atmospheric rivers. And so just the presence or absence of a few of these events can really make or break a winter season and snowpack development throughout the course of your season. So atmospheric rivers bring notable contributions to the annual precipitation, primarily along the coast, but that effect does persist further and further inland. And the persistence of that effect further inland is related to these favored corridors of inland moisture transport. So being able to pass through gaps either between mountain ranges, such as the Sierra Nevada and the Cascades, or even through smaller gaps within the mountain ranges themselves. Extreme precipitation is very strongly tied, and when I refer to extreme precipitation, I'm primarily referring to the 1, 2, and 3 day precipitation, not explicitly the short duration, high intensity precipitation events that often trigger other mass movements. That's not to say that these kinds of events don't take place during atmospheric river conditions, but when we talk about extreme precipitation and atmospheric rivers, we are generally referring to 1 to 3 day precipitation totals. They're also very strongly connected to high and very strong, or if not extreme winds. And they tend to be warmer, so they tend to have a higher elevation of that rain-snow transition elevation. They are known to drive numerous hazards throughout the upland and lowland environments, ranging from flooding to mass movements, including landslides and debris flows, as well as avalanches. And these couple figures here are from kind of one of the seminal works by John Rutz, published in Monthly Weather Review, highlighting the atmospheric river fraction to total precipitation. That's shown on the left-hand side using a gridded precipitation data set and the SNOTEL network. And then on the right-hand side, showing the percentage of top decile fraction of extreme precipitation from atmospheric rivers. And you can really see that fairly strong gradient as you move from the coast inland. So they tend to have a stronger impact on extremes at the coast, which makes sense because that's where much of the precipitation is able to take place, and we haven't removed a lot of that water vapor from the atmosphere before it moves inland. So some of the impacts and influence on avalanches in the Western US was a question that we had been asking ourselves for a while. Well, what is the tie between, we know these are really big storms and they must have an impact on avalanche activity. The challenge is we can't observe every single avalanche, and the avalanche hazard rating has all kinds of other challenges associated with it. And so what we did in this study is we wanted to try and connect fatal avalanches with atmospheric river originating storms to see if there is a relationship between the two. And what we found was somewhat consistent with John Rutz's prior work, that along the coastal regions, a greater percentage of avalanche fatalities were associated with atmospheric river landfalls. That percentage declined as we moved further and further into the intermountain and continental regions. And so all of that was rather consistent in that the big storms along the coast tended to have a larger percentage of AR fatalities. The reason for that is somewhat obvious, I'm sure, because of the tie with extreme precipitation. So atmospheric rivers contribute large of snow water equivalent or precipitation to the mountain environment. And what we found was that if we use the Perla threshold for avalanche activity of 30 millimeters of SWE change, 30% of these cases exceeded that threshold for the 1-day total precipitation, and 50% of these cases exceeded it for the 2-day precipitation. And this is based off changes in 1- and 2-day SWE based upon SNOTELs that were within a 1/4 degree of each fatality location. So we see consistency in the heavy loading from precipitation in these atmospheric river type storms were contributing to likely to the avalanche activity. Something interesting, however, that came from this is when we start thinking about the frequency of atmospheric river activity. So that's the left-hand figure. I call this the ball pit figure because it kind of reminds me of the ball pit at the McDonald's when you were a kid that you would never want to jump into more now, especially now. And what we see is along the coast, as we move inland, the average number of atmospheric river days per year decreases. What was a surprising result from this work was that the number of fatalities per atmospheric river actually increased as we moved inland. And those are the numbers shown on the right-hand figure, which is a little bit of a messy figure, I will say. Those are the values, which is the basically the rate of fatalities per atmospheric river. And you can see that those numbers go up as you move into the more interior states. So while the atmospheric river activity declined, this increase in fatalities per atmospheric river, the way I interpreted that is that these large events that characteristically contribute extreme precipitation are favoring heavy loading on characteristically weaker snowpacks. So if you get one of these large events, as you move further inland, you have a greater probability of that heavy loading taking place on a characteristically weaker and more likely to avalanche snowpack. That is totally open to other interpretations, but that is kind of what we gleaned from this analysis. Okay, so let's now talk about atmospheric river projections moving into a warmer future. As the climate warms, the ability for water vapor to exist in the atmosphere increases. So we have more water existing in a warmer atmosphere. And the consensus from numerous modeling studies highlights that atmospheric rivers are projected to become a little bit less frequent. However, they are going to become longer and wider. So they're going to transport moisture further, and they will impact a larger region. The figures on the right-hand side there show a couple different ways to visualize the historic patterns at the top, and then a couple of the different, I guess the two key concentration pathways for basically emission scenarios for the future. And then at the bottom, the differences between those two emission scenarios. So the RCP 4.5 is a less aggressive, it is a lower emission scenario, assuming more aggressive emissions reductions. RCP 8.5 is sort of the business as usual, emissions continue to increase unabated. And so between those two, we can see the differences in terms of atmospheric river moisture transport. The units are given down at the very bottom there in kilograms per meter per second, is substantially more in the warmer RCP 8.5 scenario. So we have stronger moisture transport under this higher emissions scenario. In the mid-latitudes, so that's where atmospheric river conditions are the most frequent, these types of conditions become 50 to 60% more frequent, and transport is 20% stronger into the future. Ashley Payne has a very nice summary figure based on kind of key atmospheric river landfall regions, highlighting how really North America gets to see just about all of the impacts of increases in frequency, more frequent landfall locations, more precipitation, an increase in precipitation extremes, increases in flooding, snow and ice melt from rain on snow is a rather strong connection that has been made in numerous studies on rain on snow events. In the Arctic and Antarctic regions, snow and ice melt can be tied not just to the precipitation, so the rain on snow factor, but also to interesting cases where there have been a few of that we've observed now, where downslope windstorms triggered by atmospheric river landfalls actually can result in substantial heating on the downslopes of these mountain ranges and generate notable ice melt. There was a case in 2015 in Antarctica where that took place. So for the most part, the projected changes of ARs is going to largely point towards the direction of more extremes and stronger impacts on our existing infrastructure from the lowlands to the uplands. Alan Rhodes recently produced a very interesting analysis where he used a recently published atmospheric river category method that Marty Ralph produced, where low categories tend to be more on the beneficial side, but also hazardous. And then as you move up in those categories, you decrease the water resources benefits and increase your hazards, either due to flooding or other mass movements. On the left-hand side here, we can see that these are the historical period. And so largely the majority of our atmospheric rivers tend to be in this beneficial to balance of beneficial and hazardous in terms of, and the AR category, I should say, is developed through a calculation of the atmospheric duration and the maximum vapor transport. in a warming world, you can see how the distribution starts to shift upwards and to the right. So we have an increase in the number of hazardous and slightly beneficial and primarily hazardous events. And then you can also see that there's a number of events that sort of go off the charts in this warming world, because as we have more water vapor available for transport, we are able to produce these greater maximum IVT values, and that will be realized as much enhanced precipitation in mountain regions. Using California as an example, where we have an extremely variable climate to begin with, the projections for future precipitation are a little bit difficult to interpret at first glance, because the projections of total precipitation don't really change a whole lot. There's almost an even split between models that project an increase in precipitation and models that project a decrease in precipitation. But where consistency begins to emerge, and this is a little bit of a scary result, is that there's much stronger consensus between models suggesting an increase in atmospheric river-related precipitation. So that's that middle figure that shows how it's much more consistent in an increase in AR-related precipitation. The non-atmospheric river precipitation also goes down. And the way to interpret this is that we see these events and they're kind of extreme to begin with historically, but we're going to see more of these extreme events going forward. And as a result, we're also going to see more variability, because if we expect less precipitation from our smaller kind of run-of-the-mill storms, and we're more reliant on these extreme storms, if we don't get those in a given year, that's even further going to drive this difference between a wet and dry year. So a few other ongoing and projected changes that we've been seeing in mountain weather and climate that you guys are probably well familiar with, but hopefully this gives you some nighttime reading to look at, is we've been seeing decreases in springtime peak snow water equivalent. Those trends largely are going down. There are a few places where they are going up. Once you start to look at the root causes of these sweet trends, there's a few different processes that can largely be ascribed to why we are starting to lose our snowpack. Snowpacks are also taking longer to accumulate, and they're melting earlier. And so in some locations, we may not have a snowpack at April 1 any longer. It's taking longer to begin accumulating snowpacks. So we are actually persisting even longer during the early season with these very shallow early season snowpacks that not only does that sort of favor the development of weak layers or basal faceting, it also plays into the human factor in that we have a reduced area to recreate in. So we have more people getting pushed into middle or higher elevation terrain where there is sufficient snowpack to recreate. This is just some examples from Oregon using a newly available snow water equivalent reanalysis that is actually available for the whole United States. So if your area, if you want to produce figures like this to kind of start looking at the conditions in your area, this data set was just recently released a couple of years ago. A big driver in the loss of our snowpacks in the Western United States is that precipitation is now falling as rain rather than snow. And those trends are the largest we found in the springtime, which is kind of interesting. During the fall, that upper figure on the left-hand side, the trends were kind of the strongest in the Great Basin, southern Utah, and in a little bit in the northern Cascades. The core winter season trends were fairly widespread, as were the full cool season trends, but it was really the most notable trends were taking place in the springtime. And so if we are seeing increased rain on snow types of events in the spring, where we have a lot of available radiation when it is not precipitating, that is able to start kicking off the snow albedo feedback, where you start melting snow out of areas and warming up the environment and accelerating that snowpack loss. And so as a result of this, we are losing snowpacks earlier in the season, and that water is coming out a little bit earlier, which has numerous effects on the water resources and other sort of downstream effects, but it is also making for not as high quality of spring ski conditions when we lose those freezing nights, and instead we're starting to see what previously was snowy, a couple inches of snow that would fill in the sun cups, and now it just sort of continues to contribute to an overall isothermal snowpack, which is not as much fun. We're also seeing projections for an increased number of dry days, and that goes along with the other figure I showed, in that we're projected to see more precipitation from atmospheric rivers, a decrease in precipitation from non-atmospheric river storms. And I believe that the interpretation there is that the loss of those smaller storms is really because those days are no longer having precipitation occur on them. And so we're having more frequent dry days, so sitting under high pressure conditions, or just no precipitation taking place. And the way I interpret that's providing us with additional opportunities for snowpacks to weaken, to be exposed to sun and forming melt freeze crusts, near surface facets, with shallower snowpacks overall, additional opportunities to further develop the temperature gradient driven metamorphism. And this is largely an impact in the mid-latitude regions. So if you zoom in on the right-hand side there, you can see that these impacts are fairly widespread across the mid-latitude Western United States. Alaska, on the other hand, is projected to get a bit drier, so a decrease in the number of dry days. South America as well. So if you enjoy skiing in the Chilean and Argentinian Andes, large numbers of increased dry days are projected for that region. So a couple glimpses into the future of strange events that we've also been seeing, which kind of adds to the weirding concept, is we had an event in 2018, which originated as a tropical cyclone in the far Western Pacific that was ultimately entrained into the mid-latitudes and made landfall as a very strong atmospheric river that had 13,000 foot snow levels. So almost all of the mountains were receiving rain at this point, just the very highest peaks, and that triggered numerous strange situations with debris flows, and there were landslides, there was high elevation flooding. This was a very strange event, but it is one that we also are expecting to see more of in the future, as projections for a warming climate, warming oceans are consistent with increased frequencies of tropical cyclones forming and increasing the probability that those will be entrained into the mid-latitudes and can ultimately make landfall. A storm of the future was what we sort of expect to see more of. Took place a couple of years ago in most of Cali. It basically impacted all of California, and then later impacted parts of Arizona and New Mexico. Very large avalanche cycle took place on Mount Shasta in this case, and there was some interesting interpretations that were made possible by the scale of the atmosphere, or scale of the avalanche, which registered on the seismic network and allowed us to tightly constrain the timing of this avalanche and kind of reinterpret the meteorological conditions associated with it. But the scale of the atmospheric river was on the maximum level of the AR categories, and kind of gives us a picture or case study of what we can perhaps expect to see more of going forwards. So a few take-home climate change red flags here, and I will keep going for the sake of time to just briefly introduce the possible compounding effect, which is a thought on the human factor as we lose our area to recreate in at lower elevations as a result of the total summation of these climatic changes. And I am completely open to interpretations on whether my interpretation is totally wrong. But the way I've kind of been thinking about this is, historically, we had a lot of safe area to recreate in, and we could kind of leave the higher, more complex terrain alone. As we warm up and we reduce our snowpack and increase our variability and kind of overall increase in our avalanche hazard as a result of these shallower snowpacks, more variable weather and climate patterns. We get pushed into higher elevations. We have more people being pushed into there, triggering several of the heuristic traps that unfortunately repeatedly take place. And by the end of the century, where we have really lost a lot of that low elevation, safer terrain, we're kind of stuck in these highest elevation, most tricky to navigate, and greatest risk regions. So with that, just leave you with a few concluding remarks that we're seeing changes largely that are projected to continue, warming and drying and more variable, persistent dry and extreme wet, and sort of this whiplash between them. Snowpacks are becoming shallower overall, occasionally deeper, but largely we're losing snow, seeing larger storms. Atmospheric rivers are kind of one key lever to really drive that change. And we're also seeing big changes in our backcountry environments in terms of who's using them. And so with that, I'd like to just leave you with the thought of, as our extreme events become more episodic, how are we going to manage this as we get pushed into an increasingly confined, busy, and potentially sketchier landscape? So with that, thank you very much.
Thanks, Ben. That was great. I particularly appreciate the speculation and the relationship of human factors and changing climate and being pushed into the alpine. I definitely have questions about that, but let's take some questions from the audience here. And it looks like NZ Snow Safety has a live question. You can unmute.
You can talk, NZ Snow Safety. I've unmuted you. But you're going to have to unmute yourself first. I can't get you all the way there.
Maybe it was an inadvertent hand raise. We'll come back if we need to. But we have another question here. And so this is an interesting question. The question is, wouldn't tree line expand in elevation due to an increasing or increasing in longer warm days? And how might that affect your speculation there on being pushed into the alpine?
So that's a great question. And I think that one is well answered by the time scale at which that process takes place. So we know to ski nice trees, they've got to be 20, 30, 40, 50, 100 years old. Everyone likes skiing in 200-year-old old growth forests, I know. So on the longest time scales, I think that is a process that would be taking place. But for our near term, I don't think the trees will be able to jump up in elevation and grow fast enough to really decrease some of the avalanche hazard as much as we'd like them to. And then I think combined with that, still you have this issue of more people in a smaller area. So even if that area gets a little bit safer, I'm not quite sure how the increase in use and sort of all of the related problems that arise from that. I forgot to mention that the Ethan Green and collaborators at the Colorado Avalanche Information Center released a really interesting, I think it's a blog post, and I assume that they're going to publish it at some point, just describing how the boom in backcountry really changed a lot of use patterns in their region. I thought that was an interesting perspective to kind of tie in this. But long story short, I think the tree line marching upward is going to take place over longer time scales than will really help us in the short term. But great question.
Great, thanks. So we have a question from Ben at the Sawtooth Avalanche Center, and he asks, is there something specific about ARs in general that leads to warming at the end of storms? And the second part is, any insight into if this might be a more or less or equally common feature of ARs in the future?
So that's another good question, and kind of gets at the concept of these, typically what we see are storms starting off warm with a higher snow line elevation, and then as the cold frontal region passes through, the snow line falls and we get into a colder regime. In terms of the storms ending warm, one explanation for what could be going on there would be that, and we do see this time and time again, I suppose, is that the persistence of the trough or the atmospheric wave isn't as progressive, and we kind of sit in that warm corridor for longer until the upper level jet actually kind of moves out of the way or out of the region, so that there's, I don't know if I hesitate to call it a decoupling of the upper and lower level circulations, but what we do seem to have seen is that we sit in that warm sector of the cyclone and we get the higher elevation precipitation falling as rain. And then by the time the cold front actually passes, we've lost that upper level support. And so that we then sort of quote unquote end our storm with very, very little colder precipitation, colder, lower density snow, because we've just been sitting in that warm sector. And then by the time the cold air finally makes its way into the region, much of the upper level support for precipitation and perhaps the moisture has also gotten cut off. But that's a really good question. I would, and is an excellent one to examine in some of these climate model projections, because we can kind of look at those exact factors and kind of see the story of a storm in a statistical sense if we pull all the different storms from all the different models, and we can kind of get an idea of the temperature trends during the course of the storm. And I think that would be an interesting one to look at.
Great, thanks. So we'll take one last question here, Ben, and then in the interest of time, we'll move on. The question is, can ARs lead to more convective precipitation? And can we expect to see more graupel?
Another good question. Let's see. So the large moisture availability certainly facilitates these supersaturated conditions where we rime on otherwise frozen hydrometeors. And so I would say off the top of my head, and I don't do hardly any microphysics, but I think that is, I would say yes, that seems reasonable to me, that we would see an increase in this sort of potential for convective precipitation with these supersaturated conditions, a lot of moisture availability. And that's maybe something that kind of ties in with the previous question, in that we have a lot of water vapor availability in these supersaturated conditions. And while we may miss some of the heavier snowfall in the dendritic growth zone, we may switch that for more of just sort of this shallow convection that's conducive to producing graupel. So great questions. These are making me think about meteorology. I've been sort of stuck in climate land recently. So
great. Well, excellent. Well, yeah, thanks again, Ben, for the excellent presentation. And it looks like there's some chat and comments there in the Q&A. If you want to interact with that, feel free. But we will move on. And so thanks again, Ben.
Yeah, thank you all.
Yeah, and moving on. So our final speaker this evening is Dr. Christoph Mitterer. And Christoph lives in Austria, where it's currently about 4 a.m. So his talk is pre-recorded. And Christoph is a staff member of the Avalanche Warning Service Tyrol in Innsbruck, Austria. He loves powder, fern, and wet snow, and I'm not sure if it's in that order or not. But above all, he likes to philosophize about avalanche forecasts and their dangers. He received his PhD from the SLF in Davos, researching the formation of wet snow avalanches. He's the author or co-author on numerous papers in wet snow avalanches and avalanche forecasting. And tonight he'll be talking to us a pre-recorded video about wet snow avalanches in a changing climate. And as he mentions in his presentation here, if you have any questions, you can feel free to email him with any questions, and I'll put that email in the chat to all attendees. So we'll start the video now.
So hello everybody, thanks for inviting me to your web seminars. My presentation will be about wet snow, avalanches, and climate change. I'm really happy that I can share my presentation, my thoughts with you guys. To invite you, sending me comments, thoughts, questions about the topic to me via email. Ask Eric Peitsch for details about my email contact, and we can further discuss this topic. So I will start now sharing my presentation with you. And again, as said, that today's topic in my presentation is wet snow, avalanches, and climate change. I will give you first a short introduction what I did mostly during my time during my PhD thesis in Davos, Switzerland, the practical outcome of that, and we'll transition over to what that means for wet snow, avalanches, and climate change. So one of the most prominent things but it's rather important to know both how much energy or how much water I put onto my snowpack, and how much energy the snowpack can bear with its cold content. Based on that very simple logic, I introduced, together with some of my colleagues, different indices. I developed them in order that the regional avalanche forecasting programs can improve their wet snow avalanche prediction routines. In fact, that led to the most known index, which is called LWC index, Liquid Water Content Index, and I would like to introduce you a little bit more into detail to that index. This index is a purely energy and mass balance based index. With other words, we don't know anything about water flow within snow. We just have a look at the simple question, how much water is in the snowpack compared to air and water and snow or ice. From many other contributions, we know that if this amount of water content is low, we have capillary forces that dominate the water flow within the snowpack. Sam Kolbeck called that the pendular regime. At the opposite, if the liquid water content increases, water will flow with gravitational forces, or will be dominated with gravitational forces, starts flowing downwards, and we enter into the so-called funicular regime. And the transition between those two regimes is very important in terms of wet snow avalanche activity, and the transition from that pendular to the funicular regime is mostly at liquid water contents between 3% by volume to 8% by volume. That depends on density, but mostly on grain type. So for facets, for example, it's around 3% by volume, whereas for small rounds, it's more at the transition to 7-8% by volume. So if we want to be conservative, we would say that the transition from pendular to funicular happens somewhere around the 3% of volumetric liquid water content, which is actually the basis or the base threshold for my liquid water content index. It's nothing else than the bulk liquid water content of the entire snowpack divided by this limit of 3% by volume. What does that mean? If we have a look at such a normal dry snowpack with cold content conditions, so sub-zero temperature regime within the entire snowpack, we would have a liquid water content index of 0. As soon as we add energy, or as we add rain, energy that starts warming up the snowpack, or rain that starts warming up the snowpack and starts creating the first liquid water within the top layer of the snowpack, the temperature becomes first isothermal, and then water starts to exist within the snowpack. The rest of the snowpack is still at sub-freezing conditions. This would lead to a liquid water content index of below 1, simply because the bulk liquid water content of the entire snowpack is probably still below 3% by volume, even though maybe some layers here could have higher water contents. But the majority of the snowpack is still cold and dry. However, if we keep on putting water on our snowpack or adding energy due to high air temperatures or solar radiation, we will continue to warm up the snowpack, continue to produce or send water into that snowpack, and this will penetrate deeper into the pack until it reaches the bottom of the snowpack, and the entire snowpack becomes isothermal and wet. And this would indicate a liquid water content index of larger than 1. In order to calculate, to know this index, we need this energy balance, we need the snow height, and we need a snow cover model such as for example snowpack or crocus, to really simulate all the complex interactions. We can go also into the field and sample this transition from pannular to funicular regime. We did that once during a major wet snow avalanche cycle in Davos. It was the spring 2010, together with Frank Techel from the Institute in Davos. We started on south-facing slopes between 2,000 and 2,300 meters, sampled liquid water content with a Danot capacity probe, and recorded snow temperature. And at the beginning, we had really the same situation as in that sketch before, sub-freezing temperatures at lower snowpack layers, isothermal state in the top layers, and the first layers got wet for the first time. And as time went on, high temperature and solar radiation, so high energy input, created or continued to warm up the pack, creating an isothermal state for the upper half of the snowpack and allowing water to penetrate deeper into our snowpack. And you see that, for example, in the afternoon of the 19th, water penetration reached pretty much half of the measured snow profile. At the 20th of March, we had the first afternoon with full penetration of the pack. You see that the water flow was very heterogeneous, but most parts of the snowpack had a slightly wet basis, and this was the time where a wet snow avalanche activity bumped in or really increased sharply. In fact, the next 3 days we couldn't go out for safety reasons. Really, almost every wet snow avalanche path on south-facing aspects in the region of the Vos vent. And the first day we really could go out was the 24th of March, and on that day we had the full penetration of higher amounts of liquid water contents throughout the entire snowpack, but this full penetration did not react any longer with the snowpack itself. Most paths already went, so were kind of empty of snow, and avalanche activity decreased. So the corresponding avalanche activity index for that cycle is here. So you see, really with the afternoon of March 19th, we have the onset of avalanche activity, and the fact that we knew energy impact and the state of energy within the snowpack and the water penetration allowed us to really forecast or predict that massive cycle here. So concluding, to understand something about wet snow avalanche formation, we need to know the energy, at least the energy input or the input of water towards the snowpack. We need to know if there is enough snow on the ground, and we need to know when this energy input or the precipitation interacts with the snowpack in such a manner that the snowpack is penetrated, wetted for the first time. So we did that, as I said, with snowpack. We modeled that with different elevation bands. You see here an example for the winter 2011-2012. On the y-axis, you see the liquid water content index. Again, as soon as this index reaches the threshold of 1, we have gravitational forces dominating the water flow within the snowpack. So the water is routing very fast towards the bottom of the snowpack, creating mostly instabilities at the interface snow-soil or at basal layers. The 3 simulated elevation bands corresponded nicely to observed avalanche activity. We had one first cycle at the end of February, beginning of March, with starting zones in around 2,000 meters of elevation, and a second cycle a little bit later in the season, by mid-April, for starting zones in the Alpine, so above 2,000, 2,500 meters. So if we want to say something now about wet snow avalanche and their formation, we see it's crucial to know how much snow is there in the starting zone, how much energy is supplied to the snowpack, and how much water will drain how fast into the snowpack. I started to ask myself, together with Sasha Belair and Ben Reuter, 3 different questions concerning wet snow avalanches and climate change. The first thing is, climate change is already happening, so is there maybe already a trend in the past? Can we see already some patterns? And we dug a little bit in the literature and found some interesting stuff on that. Then the second and very important question is, will there be snow in the future? Without snow in the starting zones, there are no avalanches, neither wet nor dry. So we will take a closer look to that. And then we asked ourselves, how does the weather look like in the future? We are talking about climate change, but in fact wet snow avalanches are natural hazards or mass movements that heavily react on a temporal scale which is much smaller than climate. It reacts on weather instead of climate, and therefore I would like to give an outlook how weather patterns that are associated with wet snow avalanches might look like in the future. And I have a disclaimer on that. Everything I gathered is more or less valid for the European Alps. I'm not an expert for regional climate models in the US and in Canada, so North America. So what you see now is maybe a little bit biased towards the European Alps. So first of all, we have a look into the past. So is there already a trend with wet snow avalanches? And there is actually a very nice work by Christine Pielmeier and Frank Techel. They presented that at the ISSW in Grenoble 2013, where they explored their massive data set of observed avalanches in Switzerland. So you see here the records of dry and wet snow avalanches from 1951-1952 to the winter season of 2011-2012. The blue area depicts the proportion of reported dry snow avalanches, and the red represents the area with the proportion of wet snow avalanches. The black line is a 5 years moving mean through that data set. And first of all, you see that every season is different. So we have a seasonality that varies a lot, high variation between different years. For example, in this year we had high proportions of dry snow avalanches, reported dry snow avalanches, almost 90%, versus next year where it was like 50-50 in the proportion dry versus wet snow avalanches. Despite that high variability, seasonal variability, or annual variability, not seasonal, we see a slight trend that from the mid-late 1980s, the proportion of wet snow avalanches is increasing. And goes down here and decreases a little bit and increases again. This is especially pronounced for avalanches recorded in mid-winter season, so from December until February, for example. There we have even a stronger increase in proportion of wet snow avalanches. Similar results were obtained by our French colleagues. They have also a massive database, especially with extreme events, with long run-out distances, mostly hitting the valley bottom. So you have here a data set that is biased towards larger events. And you see here the proportion of powder snow avalanches that decreases from about 25% in the 1970s until, let's say, around 15 to 10% for the years 2005 until 2010. Again, the variability, the annual variability is quite large, and also the 5-year running mean shows some variability. You have, for example, here, the famous 1999 avalanche winter in Europe, which creates a larger spike towards more powder avalanches, more extreme avalanches reaching valley floors, but the general trend is decreasing. This data set has another flaw. It bases the typology of the avalanches mostly on the observed runout. So a wet snow avalanche could also start dry and train some wet snow and reach the valley bottom as a wet snow avalanche. So this data has, of course, its limitations, but both data sets show actually a slight decrease in dry snow avalanches and an increase in the proportion of wet snow avalanches. Last year, Ben Reuter, Sasha Belair, and I tried to approach this trend pattern a little bit different. There is also a very nice talk by Ben Reuter and Sasha presented during the virtual ISSW. You can see the presentation with its recorded video on that for more details. What did we do here? We used modeled snowpack, again performed with the two models Crocus and the Swiss model snowpack, to analyze periods where persistent, non-persistent, and wet snow problems prevailed. So all bars with the light bluish colors represent the days or the amount or the count of days with avalanche problems on persistent weak layers, the green one on non-persistent ones, and the red circles show the amount of days with wet snow avalanche problems. You will see no distinct pattern, so there's no shift from maybe more days with less days with persistent problems to more days with wet snow problems. It's simply random, again, high annual variability. What you do see, though, is that the onset of the wet snow or wet snow avalanche problem kind of starts earlier. So that's representing by that line. It's connected to this y-axis on the right, where you see the day where we had the first activity of, or high activity of wet snow avalanches within the last 20 years for the region of Davos, so again inner Alpine. And you see from around the beginning of May it dropped to let's say the third week of April, more or less. So we have 2 weeks of shift, and in general in the last years wet snow avalanche cycles tended to start 10 days to 2 weeks earlier than 20 years ago. So that's what we kind of found in the past, and we see already, even though we analyzed more or less short periods of time, for example the 20 years here wouldn't be enough for a climatic period of 30 years. The other two data sets would fulfill that requirement, but still in that very short period of time, climatic wise, we see that trend that something has happened. So we have more proportion of wet snow avalanches, and wet snow avalanche cycles tend to start earlier in the season. So what's about the snow? Will there be snow in the future? And there's another very nice analysis by Christoph Mitterer, again from Davos. He and his team explored the snow cover data sets and snow cover modeling for the future. So snow cover models coupled with regional climate models to kind of see the duration of snow covers nowadays and predict them for 2100. And that's depicted by those boxes here on the left and on the right. You see the duration of the snow cover at present for north and south facing slopes, and you see that already now for south facing slopes below 1000 meters, we will have, or we generally have, only 40 days or less than 40 days of snow cover. Most of the elevation and aspects are still green, but what's about the future? And for the future, Marty and his colleagues predict a clear trend towards higher elevation snow covers with less days. So on south-facing slopes about 2000 meters in the European Alps, in 80 years we will have only 40 to 100 days of snow cover. There's still good news. You see the green bars in the high alpine, so above 2,400 meters on south and north facing slopes. There are still signals, trends showing that the snow cover duration is 100 days and more. And that's actually where in the Alps we have the most starting zones of larger avalanches located. So bowls within that elevation band between 2.5 and 3,000 meters represent the characteristic starting zones for large and very large avalanches. So on the one hand, good news, we still can go skiing in 2100, and on the other hand, there is probably still enough snow for producing larger avalanches in the respective avalanche starting zones. So what does the future weather look like then? And this is very important because, as I've shown at the beginning, we need to know how energy or water is transferred to the existing snow cover. So we know that a snow cover will exist now, or we are pretty confident that it's going to exist in the future, at least in the elevation band representing the starting zones. So now we want to know something about the future precipitation trends. And there is, again, from Switzerland, from Meteo Swiss, a very nice analysis by Frey and his colleagues in the cryosphere from 2018, where they used different multimodal approaches to predict at the regional scale the precipitation patterns in the future, so for 2100 again. And I picked out here two parameters. First, the mean snowfall, that's the upper row, and second, the snowfall fraction, so again, the proportion between snow and rain, more or less. The black lines and dots represent the reference simulations. The purple one is a simulation without a bias correction, and the orange one is with bias correction. Let's start with the mean snowfall. You see that, for example, the dependence of snowfall to elevation predicts for the future much higher mean snowfall events for all elevations above, let's say, 1000 meters. The bias corrected version is, sorry for that. The bias corrected version, the orange one, is a little bit more conservative and follows more or less the actual situation, so no change at all with in the next 80 years. If we look a closer look into the seasonality, so the amount of mean snowfall for the months September until May for different elevation bands, so below 1,000, between 1,000 and 2,000, and above 2,000 meters above sea level, we see some differences. Again, the orange biased corrected multimodal approach predicts more or less the same outcome as the reference one. The only difference is here for the elevation between 1,000 and 2,000 with slightly higher values for December, January, February, and March. But the purple one, the not corrected multimodal approach, really predicts a massive increase in mean snowfall. So you see that even for lower elevations, we get a prediction of more snowfalls, more mean snowfalls for the winter period, and this with, of course, higher uncertainty is the case for higher elevations as well. The snowfall fraction, though, has a little bit another signal. Here, again, for the not corrected version, we see more solid precipitation, especially in January, February, and March. For the corrected simulation runs, the orange ones, we see that we will have more rain events than for the reference periods, at least for elevations below 1,000 meters above sea level. For the other elevation bands, almost no change is happening. So Frey and his colleagues kind of tried to capture those patterns into these two graphs, where they see that where they use this probability density function over temperature. You have here temperature to kind of predict or to say or to analyze where most precipitation is happening at the moment. For low elevations, this is mostly between 0 and 2 degrees Celsius, so below 1,000 meters, most precipitation is already happening as rain, and to a lesser extent, between -2 and 0 degrees Celsius, occurs as snow. And this shift will be even heavier for or more dramatic for the future scenario. So we will have only a very small amount of precipitation within the temperature regime of snowfall. Most of the temperature regime will be in a mixture of rain and snow, or even as rain on snow events. We have a little bit different pattern for the future scenarios of high elevations. So at the moment we have most precipitation at very cold temperatures, creating low intensity snowfalls at higher elevations, that means in the Alpine. And the highest intensity of snowfalls is reached again for this band between -2 and 0 degrees Celsius. And our colleagues from Meteo Swiss predict that most precipitation will shift towards this band, and we will have to expect more intense snowfalls in the future. So future precipitation trends, to sum that up, we will have more extreme snowfalls, especially at higher elevation. That means that extreme precip in the Alps will be more frequent and more intense. We have the feeling that this is already happening. For example, a couple of weeks ago, during the first week of December, the south face, or the southern border of the European Alps had a massive precipitation snowfall event, recording 300 centimeters of new snow within 48 hours, which was never recorded in the years before, and the records go back until at least the 1960s, in some places even until early 1900. So it was a massive event. Will there be more extreme rain and snow events? There is a slight pattern that also midwinter we will have rain and snow events at increasing elevations. At low elevations we will have more rain, but this is again connected to large uncertainties. So I come to my end, to the conclusions. Again, we connected the formation of wet snow avalanches to climate change. We found out in the past data that at low elevations, avalanches will run shorter or less frequent, and deposits are more often wet. It was within the French Alps. We have a higher amount of wet snow avalanches compared to dry snow avalanches, especially for mid-winter periods, and this is true already since the late 1980s. We have at high elevations snow-covered depth and new snow amounts that persists. We have some trends that are indicating some future projections. For example, the onset of wet snow avalanche cycles at the season is starting earlier. And we have an ongoing wild discussion on the severity and the persistence of weather patterns, especially connected to precipitations. Do we have longer periods with precipitations? Do we have shorter periods with higher intensities for precipitations, changes from snow to rain, forth and back? This is observations that are on the way, and I think we will need some more years to really understand whether climate change is impacting weather patterns in such a way that we will have to expect maybe more wet snow avalanches. With this, I conclude. I hope I could give you some insight into our thoughts about wet snow avalanches and climate change. Hope you enjoyed the talk, and again, I would like to invite you to share your comments, thoughts, and questions with me. Send me an email, and with that, I finish, and I wish you nice other presentations. Bye-bye, and have a nice day.
All right, thanks Christoph for that, and I put Christoph's email in the chat, so if anyone has any questions, you can direct those to him. And thanks to all of our speakers, to Ben and Pascal, and to all of you for attending this evening. We really appreciate, especially those of you that hung on till the end. We know it was a long session tonight. Hopefully it was worth it. And we do have another session in February. Look for emails from Dan about the date and time on that. And thanks again to everyone, and we'll see you next month.